So he's currently Professor and Dean Engineering and Computing at University of Central Lancashire. Professor Fernando is also served as the Dean of Strategic Development and Dean of Faculty of Architecture, Computing and Engineering at University of Wales Trinity St. David. Professor Fernando is a chartered engineer and a senior fellow of Higher Education Academy. He's also led a multidisciplinary portfolio of undergraduate programs offered in School of Engineering at Manchester Metropolitan University. He is an experienced engineer, academic, and academician, consultant for transnational education, and an industrial consultant for electromagnetic capability. He is an RF engineer and his research expertise is in the area of using microwaves and millimeter waves for imaging purposes. His latest research is in exploring AI-based image processing solutions for climatic resilience. His research career has been supported by grants and funds from various organizations like Military of Defense UK, Wellcome Trust, and his council, etc. His last research grant is a successful higher education investment and recovery bid to the value of £4.75 million to start up a cross-faculty enterprise project. Professor Fernando is a senior academic leader with a proven record of accomplishments in higher education leadership. He has experience in leading change management and strategy implementation of research and academic success. So we are very glad to be with you, sir, today. I welcome Fernando for his keynote. Over to you.
Thank you for the kind introduction. As I was introduced, my name is Fernando. If you're coming in, come and take a seat. There are lots of seats in the front. What we're going to do today, in the next 40 to 50 minutes, is have a topic based on artificial intelligence, but more importantly, talking about how that has been got to this far throughout my different research projects with different research groups. So I'm hoping that at the end of the presentation, I'll take questions, time for questions, but if there are any questions you want to ask, as we go through, just put your hands up and we can take some questions. So that's the topic for today, unlocking new frontiers in building global climate resilience with AI-powered image processing. So that's what we're working for, and that's what we will finish in as well. But in order to get there, we have to cover a bit more introduction, and then we will get into case studies, and we'll finish in good time. I don't know if anyone knows, this is called Machu Picchu. This is in the Andes mountain range in Peru, and it's a civilization called Inca civilization, like in India where we have lots of civilization, ancient civilization. In South America, in Peru, this is one of a very ancient civilization. So we're talking about 450 or 500 years ago, 1450 I think, and the picture you're seeing there is actually a temple for their civilization, and all the people in that mountain area, it's a very hilly, it's like our Dharmashala kind of place, lived around there. In early 2000, can I just check, if I move away from my microphone, can the people in the back, can you hear us? You can, thank you. So in early 2000, an organization called Engineers Without Borders, which is a UK-based organization, received a project request from local NGOs in there, asking for UK experts, or mostly UK students, because obviously if you get a consultant from experts, it will going to cost a lot. So they requested the UK student experts to come and build some construction for them around this area. Not in there, because this is a UNESCO site, you can't touch it, around that. And as you would expect, the students from Oxford, Cambridge, all the well-known imperial, all the well-known places came back together. These are the creme of the creme in the UK, and they did a good job. They started the project, planned the project, finished the project, and handed over back to the locals within the time frame, 6 months. It was a construction project. But 2 years after the project, the project lead got a call. And this is from the local people. And they said, well, the construction you did for us, I'm afraid it's becoming unstable. The construction is not. And the UK experts were like, oh, surely not, it's not a problem, because we've done all the research, we've done all the calculation, structurally it's sound, and it can't be. And they were both were saying, well, actually, when we live in it, it's not very secure. So something has gone wrong. So throughout this presentation, we are going to think about what is it that made that project failure. But in answering the question, we will answer the first slide, unlocking AI to understand better. Okay? So I'm going to touch this slide at the very end of my presentation. So I'm not going to tell you why it failed until then. Just about myself, my name is Fernando. I was born in India, had a home in Dubai for a while before settling in UK. I went to study in UK, and then I got married and kids and a job in there. I currently lead a school of engineering and computing, and it is a very large school, one of the largest school for post-92 university, and we turn over about £40 million every year. And the school covers quite a lot. We do astronomy and astrophysics. So this is looking at, we have two planetarium and one planetarium and two observatory in the school. What that allows us to do is to look out for new planets and new objects in the space through our astrophysics. We also do civil engineering, fire engineering, energy engineering. Our fire engineering is very sought out in the Middle East. You all know that Qatar hosted the 2022 FIFA World Cup. In that World Cup, 80% of the health and safety executives who worked in that World Cup were graduated from my school. Yes, sir. No, if you think I need it, I'm happy to have it.
If you want to go there.
Oh, okay, fine. Thank you. It's working now? Okay, and we also have construction and architecture, which teaches construction-related programs. We also do computing, cyber, and electrical electronics and robotics. Recently, the Ministry of Defence and the GCHQ, which is the spy agency in UK, joined together and formed a national cyber force, and we are a partner with them. And then we also do all our mechanical related program like mechatronics, mechanical manufacturing, maintenance, motorsports, and we also teach pilots. So we don't do pilot license because we can't give license as a university, but we teach students who can study piloting and then go and do the exam with CAA. So that's a portfolio we have. One of the advantages we have of having that portfolio is our research is often cross-disciplinary. Just like you guys have lots of schools, our colleagues move from one area to another area too. So that's the background of where we are, and I'm so pleased to welcome one of my collaborators, Komali, here. So our school and the university I work with, we host the UN Office for Outer Space Affairs, and it's the regional sub-office. And Komali, most of you may know, she's instrumental in bringing that sub-office to Preston and to our university. Some of the results which I'm going to show today would not be possible without that affiliation with United Nations. So what we do is, when we say outer space affairs, we are not talking about aliens here. What we are trying to say here is using satellite images to help with sustainable development. So if there is a coastal erosion, or if there is a coastal disaster going to happen, could we pre-plan, could we pre-warn people so that it is sustainably dealt with? So that's what we are trying to do. When research keynotes like this happens, we talk about lots of results, and those results don't happen by magic. Those happen because of lots of people collaborating together. And these are my current collaborators. There are so many other collaborators you will see later on, but these are current. So Kumali, you know, Professor Tupake is in Ireland, originally from Sri Lanka. Professor Sanjeev is in Mauritius, and Ms. Resma is also in Mauritius, but Resma is our PhD students for all three of us. So some of the results we will be sharing today is because of the collaborative work we do, and I'm ever so thankful for our group. Now, before I go any further, let's think about what do I mean by artificial intelligence and image processing in this context. As soon as artificial intelligence was out, everyone tried to take artificial intelligence and use it for their research. Understandably, everyone is an expert in it, and I would say I'm not an expert in that because there's so much I don't know. But what I would like to share is what I do know, which is on image processing. This is a quote from a company, it's an Indian company based in Gurgaon, and they also based in America. And what they describe as artificial intelligence is the system's capacity to carry out operations that ordinarily require human intelligence. So anything that human would do, but you're able to get a computer to do, or a software to do, and that's what they would define as artificial intelligence. Not perfect, but I'm happy to go with that. But the subset of that is the machine learning. So these are algorithms that allows us to help to predict pattern and help us to understand it. So if they were not there, what would have happened is, let's say when I started my research 15 years ago or 20 years ago, when somebody is presenting a data, you as a human needs to see whether there is a pattern. Then 10 years ago, you can tell the computer what the pattern is, and then it will go and look for that pattern. Whereas what now it does, it automatically tells you there's a pattern, and it also tells you what to look for it. So that's the difference, okay? It's not that artificial intelligence haven't been there, but that's how I am using it, and we as a group are using it. And there are plenty other examples of how artificial intelligence is used. And these aspects here is different stages of image processing. You need to capture the image, you need to quality control that image, and also distinguish that image so that you can see the pattern, if there are any, and if they don't see a pattern, then you think about the chaotic theory of that pattern. So that's how I'm going to define artificial intelligence image processing for today's purpose. How did that look visually? Well, we acquire data, and this is from one of our publications. I acknowledge the publications because it's not from me. I wanted to ensure that the people who generated that are acknowledged properly. So we have image acquisition, we do pre-processing, and then we do the image analysis. And then the analysis is where you're grouping, you're looking for pattern, and then it helps us to understand the image, what we are looking at. So if there is a medical imaging, you're looking for any disease in there or risk for an individual, this is what it helps us to do. And the next few slides, or few projects, each of the projects I'm presenting will have about 3 slides, but it took about 5 years to complete. So it's about taking what has been going on for a while and trying to present it in a way that many people can access it, but also leaving out the technical not to the nth number, but I will introduce technicality, but trying to understand the bigger picture is what I'm trying to present today. So those are artificial-based image processing definitions. Very early on in my career, after I finished my master's, I was awarded a PhD working with Cancer Research UK. So that's the next few slides are around that particular work I did with Cancer Research UK. I don't know if people know this lady here is a celebrity called Kylie Minogue. She was an Australian singer and actress in around 2000, early 2000, 2005, I think. And she was diagnosed with breast cancer. And at the time I was finishing off my my MSc and going into PhD. There was a huge grant at that time for a PhD student to be working with about £1 million from Cancer Research UK. And the reason is we wanted to understand not Kylie's breast cancer, but mostly breast cancer. How can we early detect the breast cancer? So now I'm going to talk about breast cancer detection now. It might be a sensitive subject for some because you may have family members or yourself directly impacted. So I'm trying to do this with a bit more sensitivity. So the patented technique I worked with is called synthetic reference beam holography. I will explain in a minute what it is. But what we're trying to do, what we are trying to achieve. So we got the funding secured. What we want to get to. These days, you can go to your pharmacy or you can go to your doctor and get a home, apologies, I didn't know it's touch screen. Okay. You can go to the doctor and get one of these. So this, I'm talking about female colleagues here, and then you can do the test in the home. And you can find out whether you're pregnant or not. You don't need to go to the doctors. You can do it at home. It takes a few minutes. How about we create a technology that will allow us to do the same, but for breast cancer. So that's a bra there, which is like a more magic or wonder bra. So that's what we wanted to get. So the funding is secured. Cancer Research gave us $1 million. This is where we are going. This is our direction of travel. How do we get there? Well, how do we get there is how we are going to use. So this is the literature available. What we are seeing here, this is says normal, this is says malignant. Malignant means like a cancerous or a tissue which is not benign. This graph shows the cancer cell, if it becomes cancer, the way that it will interact with electromagnetic wave, that is the dielectric constant, will be considerably different to a normal cell. So what does that mean? It says my hand has got a cancer, and this hand is not a cancer. If I put my hands up, I scan it, I will get this. If I scan this hand, I will get this. So if I know that, it is advantage to predict cancer. And that's what this graph is showing. But what is interesting is the dielectric property of a cancer cell, that is how the cell will react to the electromagnetic wave. This property shows first before even the cancer cell becomes cancerous. Okay? So what does that mean is, if you go to an X-ray, like a mammogram, which is what they do for cancer, it will tell you if you have a cancer, but this will tell you you're going to get a cancer in 3 months' time. Okay? So we got the funding, we got the mechanism, and we are going to implement that. So how do we do that? Well, we are going to scan a human breast, and then we are going to use micro signal for that, and then we are going to use a computer to detect and where the cancer is. It always sounds very simple. And as I said, each of the slides take about 6 months to actually get to what we want to get to. But what is this one? So this here, I'm going to enlarge that, and that's how it looks like. Okay? Now you're thinking, what on earth is this? Well, the official name for all of this is called Pocklington theorem, or back propagation is what I call. And I can assure you, each one of you in this room, in your life, sometime would have done back propagation. I'll tell you what. I'm going to put my microphone down. Now, this is a notebook, and I'm sure when you are younger, you would have had notebooks like this. Do you remember when we used to write the name of this notebook here? Maths, English. Do you remember that? I used to do that. So every time when we write something,
the object is what we are looking at, maths, English, whatever. But if I flick the pages, each page will have an ink of that maths, physics, and on its own, it's nothing. But combined together, it's something. And that's exactly what we're going to do. So what we're going to do is reconstruct the image of the breast, moving from the nipples to the chest wall, and trying to do a slices of imaging, not the breast. But you can then take off those imaging to predict where your tumor is without even touching the breast. So what does that mean is, if a person has got a tumor, you can early detect it, but you can also tell them, pinpoint, your tumor is either 0.5 millimeter from your nipple or 1 centimeter from your chest wall. So this is called back propagations, and that's the algorithm which we used here. And in order to get the back propagation, I need to use the phase shifter and variable attenuators in microwave to get that. And that's the setup. So once you've done the funding, you've done the methodology, you've done the theory, then you start building it up. So you've got the human breast phantom there. Insert in oil. If you've ever been to an ultrasound, for those who had babies or those who are husbands who have been to the, and they will always put a gel on you. Do you remember that? And that's what we put the vegetable oil there for protection. And then we have all of these phase shifters and variable attenuators is what I showed you in the last one. So now we've done the experimental setup, and then we have to do preclinical studies. So before we touch the human, we need to make sure it works somewhere else. For lab shots, 2 metal things, put it inside them, tie it up like as you do a cancer inside a body and all that, and that's what you get. So you are using your Pocklington theorem, the same principle, the back propagation, to get an image without even touching the image. Okay? And that's with the bigger metal, and that with the smaller metal. What about this? Apologies if this image is a bit gruesome. It's a kidney wrapped under fat. That's how our bodies look like, our internal organs. And you can find the kidney. So now we have proved that our theory works. Then we have to go to the trials. Right, we get the, this is our collaborators in America using the same technology, the wires, so the things here, or the microwave antenna, just like we saw in the bathtub of vegetable oil, and then they do clinical studies. All of that worked, and we were able to get this. So I'll come back, this is the last slide in this one. So this is what we want to, this is what we started off with, this is what we want to achieve, and where we got those clinical trials to prove it works. But in order to get to here, there were limitations. The limitations are, when people come for examination of their breast, you don't want them to stay for 6 hours. You want it to be quick and get the result. You don't want to take a test, pregnant test in the morning and wait for evening for the result, do you? No. You want to do it immediately. We couldn't do that because the limitation of our data processing. So this is what this research taught us. We got the proof ready. It still be available for patency, but we don't have the data processing power which we have now at that time. That's why we moved to AI-based imaging. So you can get a sense of what I'm trying to convey here. The results are good, but we couldn't put it in the market. The next application, now that I worked on imaging, I moved on to security applications. So this is for events and airport security. So imagine you're going to an event like G20 or G8, all the leaders are coming and they have metal barrier and you have to check through. Sometimes the metal barriers are so close to the event itself, it's too late. Somebody could carry something and then blow that up. So we have to create something that will work for security, but also for commercial. So this is a metal detector. So what we want to achieve is security here. Commercial in Manchester Airport is about reducing the time. You all know when we go to the airport, we go through the security, and then after security is where you get the duty-free shops. Of course, I'm not able to spend much money on it, but what they're predicting is every minute you save in the security queue for the people, it's £1,000 for the airport in income. So you go and get a coffee, that's income. You go and get a sandwich, that's income. You get a perfume, that's income. So what they wanted to do is to expedite this process so that it's commercially viable. Okay, so Manchester University gave us some, Manchester Airport and the Ministry of Defence gave us some money, and what we want to achieve is increase safety, that's the first, but reduce time. So we designed a thing for it. I don't know if anyone been to Manchester Airport. This is the first prototype of the screening in Manchester Airport. So I don't know, in other cities as well they might have. So you have to go and stand in the machine and put your hands up like this. I don't know if you have any been, and it does a scan of it. And this is a prototype of it. We built it with Kinetic. And what we done is using a technology called millimeter wave to predict what is happening in what anyone is carrying. But then we said, this is too big. It costs a lot of money to make. How about we make it portable one? Okay, why do we need to do that? I'll come back to that. The technology we use is called early time response method. What is that? Well, let's say I don't have a pen, but imagine if I had a pen, and every object we have in our pockets or in our hands will have a response to electromagnetic wave, just like what I did with the breast cancer. But depending on the object, if a pen will have a different wavelength to your keychain or to your lanyard or something like that, every object will have a response. But that response, the frequency at which the response happened is different. So if you know the frequency, you can tell which object it is. And they have two types of response. One is called ETR, early time response, and late time response. We don't worry about that because this is where the data is. So if I know an early time response of an object, you can tell what that object is. So we did that theory, we did simulation, then we practical. Again, every slide I'm showing, it takes about 6 months to create this, okay? It takes about 6 seconds to go through this. But we did just a different materials, so needle, steel rod, replica revolver, a kitchen knife. So this is all helping us to gain that data set. Again, data sets are important for artificial intelligence. And so this is what we did. So we used the generalized pencil of function to calculate and see if we can replicate the objects. It's only a small set we compared, but we did about 15,000 objects. And then we use something called principal component analysis to increase the percentage at which we can predict this object clearly. So if you are carrying a pistol, for example, then you can predict it with about 84% accuracy that you are carrying a pistol. The reason it's not 100% accuracy is if you have two objects, let's say this microphone and this phone, if you have it as a gun shape, it may give you similar response to a gun shape because it's the same shape. So that's where the accuracy is down. And we then, the gun on its own, not going to walk on its own to the barrier. It will always be hidden under a human or a thing. So you need to then see how that early time response will be if I put a human body next to it. And that's what we're trying to show here. So the human element object, the classification rates, some of them are very good, some of them are not so good, and that's what we got. The problem with this, I might need to know whether it works. So this is an image I'm trying to show. Let me see if I can get that image working. No, I'm afraid the image is not working in this computer, but if anyone wants to see that, I have my laptop, I can open that up. What you will see here is a man with a backpack walking and turning around, and you can see his image there. The image is very crude. So we have the technology, we have the understanding how the technology works, but for our capability of the data processing power and the capability of not able to integrate many other technologies in it, what we can achieve is limited. It's important for the safety and for Manchester Airport, but it's not right there yet. And this is why AI-based imaging will help us to get this better. So, the next project. This project is 2015, something like that, and we did sustainable farming. Now you can think, where do we go from medical imaging to security imaging now to farming? Because this is what transdisciplinary research looks like. You take one, imaging is what I know, but you then fit that into many other applications. So, well, sheep. Well, This sheep is a woolly sheep, it's got a lot of wool in it. And this common occurrence in northwest of England, where we are, in where our university is, and also a big problem in Kazakhstan. I'll come back to that. What we want to achieve, always with the research, you want to know where you're going. We want to achieve a financially cost-effective solution for the local farmers. That's what we want to go to. Okay, how do we getting there? Well, let's talk about in farming. They have something called sustainability, sustainable farming. What does that mean? Is everything. I think in India we always have that saying that everything comes from the soil; it will go back to the soil. Of course, they're talking about humans, but it is true for everything else as well in the world. So we go from the compost to raw materials to the sheep itself, go for the processing, make the garments, and then one day it goes back into the soil. So that's called the soil to soil sustainability. What is key here is the local knowledge. When we approach these farmers, we were coming with our Pocklington equation, which I showed you, back propagation, early time response and all that, and all they're saying is, I don't understand any of that. All I need you to tell me is, when I take the wool of this sheep, I need to know whether that wool is a fine wool or a coarse wool or a wool which only can be used for a rug. If it is a fine wool, you can make it into a jumper, like a clothing, but if it is a coarse wool, you can use it for insulation. That's all they wanted to know. They don't want to know about all these technology you use to get there. Doesn't matter what you do. Right, how are you going to get there? Well, before I get to that problem, I have a Kazakhstan problem. Now, this is how the wool look like. So this is the difference on fine wool to the coarse wool, different types of wool. If you know what your wool, the quality your sheep is producing, then you can sell this to companies. Kazakhstan is a large country with a lot of sheep. There are more sheep than humans there, and they have a problem. They shear the sheep every year, and they become huge quantity. They don't know what to do with it because the country is not that well developed. It's only 25 years in independence. And along comes Turkey. And Turkey says to Kazakhstan, you know the waste you got, the wool, don't worry about it. We will take it off you and we will pay you money. And they did pay money for Kazakhstan to take it off. And Turkey turned that wool into garments and sell back to Kazakhstan for 3 times the price of the wool. So you can see the problem. Okay? So you all think that research is research, but research is geopolitics as well. Understanding how the policy will influence. So Kazakhstan is a new country, new ministers. They're thinking, well, we have a problem. We are selling our own raw product and buying it back 2 times the price or 3 times the price of the same product. So we have to provide a solution. But the country is very poor. They can't afford the 1 million pound grant of that massive amount of machines. They can't do that. So we need to create a localized solution. And most of you, if you are in computing and electronics, you would have come across microcontrollers, or in sense, not Raspberry Pi, I'm thinking about big microcontrollers. So we used some of that to help the local farmers. So what we are able to do is using the simple technology of capturing the diameter of the wool. So if I know the wool and I put this handheld wool counter on top of it, it will tell the farmer what kind of wool they have, whether it's a white wool or a gray one, or what diameter it is, and it can measure up to 10 micrometer. Very simple device, very capable, sustainably sourced and helpful for the farmers. So we proved that this is our product. This is wool counter. It can go up to 1 micrometer. It costs up to £100. But compared to all the other money, where is £50,000? Where is £100? If you are a farmer, you will buy one of that and do it yourself. And that's what they were able to do. So that's the wool counter, and some of you may know how to do this. This is my student called Chris Boyd who did this, and you go and put it on top of the wool, and it will tell you how thick the wool is. The thickness of the wool you can then determine whether it's a fine wool or a coarse wool or a semi-coarse wool. And that is what we were able to do. And we were only able to do that because of the local knowledge. Because if the farmers weren't there to help me, Mike, I don't need your Pocklington equation. I don't need your principal component analysis. All I need is something to do this. I would not have been able to do this. So AI is very good, but without local knowledge, it is limited. And I'll come back to that why, because we are going to answer the question in Machu Picchu. Right, so that's 3 case studies done. I don't know how am I doing with time, but this is the last case study, and then we'll coming to the home straight. Right, climate resilience. So this is the newest research, Komali and our group are excellent doing this. And before I get into that, we also know why this is important, isn't it? Well, coastal erosion, you all know it happens, and it's a big issue. The climate change, this is in India itself. All these were from Komali's and her research. And this, I think this is in Vietnam. Is that right, Komali? This is in Vietnam, isn't it? Yeah, every country impacted by climate change. And when I say climate resilience, is how do you approach that using AI and image-based processing? And then we have our own UK. It's important to know that UK is made up of 4 countries: England, Wales, Scotland, and Northern Ireland. This part is not actually England, this is Ireland. So this is UK, is all of them, and then England, Wales, Scotland, and Northern Ireland are part of it. In here, in this picture here, what we're showing here is the climate is warming, sorry, the earth is warming, and because of that we are experiencing drought in terms of water and water shortage, and that has been the worst since 1935. And that tells us that there is extreme weather patterns, and we are trying to understand if in using image processing whether we can solve any of this. Oh, great. No worries. Can you hear me?
Yes.
Okay. Well, I don't even have the printout of that, but I have it in my laptop. So, what shall I do, sir? Shall I take questions until then? And then we can pick it up, the climate resilience. So, if there are any questions you wanted to ask me while we wait for the power to come back, we can do that. Yes.
Myself, Dr. from Scope.
Yeah.
Actually, I have a doubt when you are using that wool counter device. Is there any scanning devices are there like camera or
Yeah.
what kind of sensors?
Capacitively charged couples. So it's simple to a camera. You take a picture, you then analyze it. But the analyzing is where a microcontroller helps us. It's just a very simple. As I said, we went in thinking we have to do back propagation, we have to do this and that. And the farmer said, all I wanted you to do is to tell me what it is. The normal camera doesn't allow them to analyze it. It gives them a picture. Then somebody has to analyze it. So all we did is take a picture and help them analyze it, and then simply say that fiber is 30 micron thickness or 10 micron thickness. And then they can make localized decision. Yeah, it's a capacitively charged couples is what we have used.
So they have to load those images into that device?
No. You shear the wool from the sheep, you put it on a flat surface, and put the device on top of it. And then the device has the camera to capture it, and then tells you. Because before artificial intelligence, remember we used to have fuzzy logic. Yeah? And the fuzzy logic is, it learns, like machine learning. So the first time there was only 3 components, like, you have only 3 types of wool. But the more you scan the wool counter, it learns. And then it creates a database. And that's what fit into our AI background. Does that make sense? Yeah. You okay? It's always when we need the most, it will say, I will take my time to come out, isn't it? So just to give you for context, we're on slide 41, and I only have 49 slides, so we're nearly there in the home stretch.
Where is your project on the projector? That's better.
I think we are back on track. So, well, sorry about that delay. So, this is where we are. So, what we have here is the map of UK, and I mentioned about how the UK is made up of 4 nations and the drought situation. And we wanted to do something about it using our own research and image processing. I come in from the image processing expertise. Kamala is our coastal erosion consultant, and she also is the co-director of the UN sub-office in our university, and also our partners in Ireland, Upake, and in Mauritius, Sanjeev and Reshma. So what we have here is I'm presenting some of the researches our collaborators have done. Some of these researches I am personally involved, some of them I'm not. So every time when I have taken an image from our collaborators, I just wanted to acknowledge them, and I have put the link for it if anyone wants to know more. Now, because of the the climate change and the climate resilience needed, in order for the local people to make localized decision on what kind of crops that they can use their soil for, you need to know the soil temperature. Now, soil is everywhere in the world. How on earth you are going to find out what soil works for what, unless you don't know the local knowledge, right? So this is research which was done in Nukus in Uzbekistan, and again using the data that is already available. So this is not new data, so the technology is new, but the data is old. But taking that into a data set, doing a data cleansing, using AI or machine language part of the AI to predict the soil temperature for that area. Because if you predict that, then it will allow the local farmer to know what crop they can put in that soil and what yield they can expect. Noting, we can also predict the weather pattern for that. Okay, so this is what I say about AI bringing power to the people on the ground. So this is the data sets here. Again, anyone who's interested, they have a good paper. I read that, it's a really good paper, and our colleagues were part of that, our collaborators. So that's AI-based soil temperature prediction. This is interesting because this reminds me, as I was driving to the Krishna River, the bridge, You know, you have a fantastic river growing past it. Imagine if you can understand the speed of the river and the impact of it on the crops that will be growing along the banks of it. Okay, so this is what they were talking about in this one. So it's a flow velocity, and if you know the flow velocity, you can predict the flooding, but also the sediment transport. So sometimes a part of the Krishna River might be more fertile than others, but it does move. That part of the sediment moves, which means if we can know that and predict where it's moving, we can avoid building a big building there, because we know that will be more fertile in that few years. Does that make sense? So that's what they were doing. But the difference in all the researches I have presented so far and these ones, but because they are using AI, all the researchers, the breast cancer, the farming wool, the security, uses one or two methodologies: backpropagation, general principal component analysis, one or two. But look at this. These guys went ahead and used 12 models of hybrid machine language. This wasn't possible 5 years ago. This wasn't possible because our computers weren't powered enough to do that. But AI allows us to do that. Okay, and again, this what I'm calling here is this allows for pollination of technologies. What does that mean? Is you may know machine language, you may not know principal component analysis, or you may know a hardware analysis but may not know the software, but you can cross-pollinate it because you are having somebody else trying to help you to do that. And that wasn't possible, and that's one of the reasons why the timing it took for the breast cancer to work in a bra, or the timing it took for the security time to work, is longer, because we didn't have this technology. Okay. Now this is our own student. We worked on this. This is on mangrove forest in Mauritius, and you know what the mangroves look like. But the key thing about this project is UN has been taking pictures of these forests around the world for decades. So they have got file images of these forests for 20 years. But we now have a technology that will help us to analyze those the images. Because if we know what 20 years ago would look like, we can then know the amount of corrosion, the amount of impact it had on vegetation, because we are living here, more people on the earth here. So this is mangroves are there from, I'm afraid we need to, I think how many more, maybe 3 or 4 images. Is the power back on, is it? Do I need to log in again? Okay, we are back on. Apologies, I have a laptop, but it doesn't connect to the computer directly because of it doesn't have all the ports. But also because the presentation is so long and there are lots of images on it, I can't email anyone either because I had to go to the OneDrive to actually access it. So we're on the home stretch. We will finish soon. So what we have here is this is funded by the UN. And what you're seeing, the pictures here, I know it's very small print, but what I want to say is the pictures show 2 years, but they're 2 years or 10 years apart. So if you have images from history, then you can use your machine language and AI to help them put them together and ask it to find a pattern, which will do it for you. And we couldn't do that before us because we didn't have the capacity or the ability to do that. And the early detection of changes leads to swifter local action. So for example, around the Krishna River, let's say in the future there is planning permission coming for an industry. You can tell what impact it will have based on your past and based on your future. And that's what it's important. So some of the recommendations we have made to the UN on Mauritius is if you do water sports, if you do boat tours, if you do development infrastructure all the way to fishing and crab, you can tell what impact it will have in your future. But then if you know what the impact it will have, you can then put appropriate risk mitigation in order to avoid. Not that we are going to stop fishing, but how do we do that responsibly? How do we do it in a way we know what is going to happen? So this is what allows us to be resilient in the face of climate change. And that's only possible because of the data processing power of AI. So that's the last of the climate studies. So we go back to the original question I started off with. What went wrong there is this. When the experts or the student experts from UK went there, they failed to acknowledge, they had all the calculations correct, but they failed to acknowledge the local knowledge. What does that mean is, this images here, these are built 15th century. It's still standing there. They built something 2 years ago, it fell down, or not very good. The reason being, like I said, this is similar to Dharmashala. You all probably know cricket, but when the ball goes higher in the air and Dharmashala is much higher because the oxygen level is lower and all the blah things, and it makes it different to catch the ball. That's the same thing. If you use the same bricks here, which we use, which are sturdy, they don't last because they're not porous enough, because the air needs to get through in and out of the building. And they didn't consider that. That's why their structure begins to crack. And they also had limited data processing power that allows them not able to, or didn't allow them to use to model things what it will look like in few years' time, but they're only able to predict what the structure integrity is. And finally, they didn't have the inability to cross-pollinate technology. How about using quantity surveying, which is what we do for calculations for buildings and construction management, but how do you use that alongside other technologies which are available for analysis of the porous nature of the structure? Now, that's why it didn't work, and all the above is now possible with AI. So what I presented here today is gone through the history of the research I've done, but every time when we hit a snag, we look at why it is the problem. We still use them, but with limitations. But these are the new frontiers that AI allows us to unlock. So things like going back to our local needs, understanding and feeding them into the process. So what does that mean is, if there is an issue in Mexico, you don't need an expert in UK telling you the problem solving. You need the experts in the room from Mexico telling you. The same in India as well. So the local power is built back, and the local community to solve the problem. So that's what Kamali and her team are doing, educating the local people on how they can look after their own environment. But also the data processing power is much higher, and the cross-pollination. So you may come across a methodology that is used in a completely different application, but you can use it in your application because you have the data processing capability to do that. And that helps us to build a global climate resilience, and all of them is only possible and powered by the AI-based image processing. That's all I wanted to say today. I hope you enjoyed the presentation, and sorry for the 2 interruptions, but thank you again for having me. It was a pleasure to share this with you. Thank you. I will take any questions if you have, but I think Sarah is coming to give us information.
Is there any queries from audience?
Okay, so what Kamal is saying is, when you ask a question, if you can tell who you are and what you're doing in VIT-AP, that will be helpful for me to know the context. Well, I tell you what, I will come off the podium and you can come and talk to me in person. Sometimes that might be easier. Oh, go on, Lambo.
Just out of
Curiosity.
first of all, I'm Professor Lambotharan from University.
Yeah.
You presented results for this frequency, resonant frequency.
Yeah.
Does the frequency depends on the length of the object, like the dipole effect, or does it because or does the material play a role?
Both. What we have done is, when we were using the metal objects, so material is a hard material, and the early time response is very easy because it just it pings off. I transmit electromagnetic wave, it hits the material, I receive the reflection back. What about plastic explosive IEDs, which is not metal? You may have metal in it, but it is enclosed in a plastic. At that time, we are still able to receive the response, but we have to do a filter in front of it in order to get the actual response, because otherwise we will be going in the wrong one. So for example, somebody might carry a key ring, but they might have a plastic casing in the key ring. The plastic might give out the response. I might classify as, okay, this is plastic, whereas actually it's a metal key ring, and I wouldn't know. So when we are observing it, we know from the response we are getting, we can know whether we need to use the filter or not. And that is how we are able to do it, but it takes another processing time. So it's a great question, because in Manchester Airport, before we set it up, what they wanted to do is, because every minute is £1,000 income for them, they said, how about we remove the barrier altogether and ask the people to walk in the corridor. As they're walking the corridor, they are screening all the time. And as they come to the end of the corridor, they can say, oh, actually, sir, you need to go to additional screening, but you, madam, you can go on. So then you are reducing the time. But the problem we hit is improvised explosive devices, because they don't normally use metals. So you're right, there is a challenge, additional step needed, depends on the materials, not on the frequency of response we are getting. Yeah, thank you. Okay, folks, thank you. And as I said, I'm here. If you need anything, I'll come back. Thank you.
Yeah, good morning to all of you. On behalf of VIT-AP University Management and Scope Department, and also IIC IDE Organizing Committee, faculty and staff members, and also research scholars and students, on behalf of them, I would like to thank our today's resource person, Professor Mike Fernando. I hope you have got some impressive concepts. How can we use the signals, and also how can we create medical images and also the images regarding to the security systems and farming. And he has given his previous research work, how he has done, and also the unavailability of those powerful processors those times, and how he was managed, and how that delay was happened. Nowadays we are all getting more powerful processors and also technology to get the images through the AI. He has shown with his research articles and what he has done previously. So it is a very impressive presentation, Professor. On behalf of all of us, I would like to thank once again. I hope these concepts may be useful to our research scholars and also faculty community. Thank you once again. Thank you all.
Attention please. We have a snacks break now for 10 minutes.